Hey guys, welcome back to another video on the channel. In today's video we're going to be solving a projectile motion question using vector calculus. So here's pretty much the question. You have a building here, let's say that's 10 meters high, and you shoot, let's say, at an angle of, let's say, 30 degrees with a velocity of, let's say, 15 meters per second. And you want to know its trajectory and how far it travels, so like this distance here. Or you just wanted to know pretty much the general motion of this particle, for example. So pretty much here we have to use pretty much a basic understanding of Newtonian mechanics. So the way we think about it is we're looking for a vector equation. So a vector equation is pretty much denoted with r with a function of time. Now the reason why it's a vector equation is because you both have a vertical direction and a horizontal direction, so both respective motion in those directions. So you have pretty much a function of t, let's say like g of t in the x direction, so x direction is denoted with I using our vectors, and we also have motion in, like, let's say the vertical direction, so a function of time as well here. So we're looking for some function like this, where if you input a time, you're going to get a corresponding horizontal position and a corresponding vertical position. And as we can see here, it's going to reach some maximum and slowly decrease over time. So we can see that this here will always increase because it's going to go in this direction here. But we can see with our function here in the vertical direction, it's going to hit some maximum and then it's going to slowly decrease. So we're going to expect some polynomial with at least a degree of 2 for our h of t. Now, you're probably wondering, how do we even start a problem like this? Well, we need to first off look at acceleration. So this all goes back to the idea, if you have a position function, if you were to differentiate that with respect to time, you would get a velocity function. So it might be represented as x dot of t, but that's also equivalent to the velocity, because the rate of change of position with respect to time is the definition of velocity. And if you were to differentiate this again, so with respect to time, you would get acceleration, because the rate of change of velocity with respect to time is acceleration. So it's represented as x double dot, or just acceleration of t, or in other words, the second derivative of position. So using this fact, we're going to go pretty much backwards. So looking in my x and y direction, I need to think of pretty much acceleration that's acting on it. So unless they specify air resistance, assume there is no acceleration in the horizontal direction. So pretty much the acceleration will represent as, alright, the second derivative of position. Now I'm going to use x because that's horizontal with respect to time. So the acceleration in this direction here is 0. Okay? Now what about the vertical? Well, we're assuming this is happening on Earth, so we have gravity. So the acceleration will be 9.8 meters per second, unless they specify as otherwise. So our acceleration, so the second derivative in the y direction with respect to time, it's going to be negative g, where g is 9.8 meters per second. Okay? So in other words, our acceleration function for our vector will be like this. So r double dot of t is equivalent to pretty much 0i plus negative g j. So all this is telling me is the acceleration of my vector function only acts in the vertical direction. Okay? Now, what we can do is pretty much, we want to work out our velocity function. So I'm just going to write my acceleration function over here. So r double dot of t is just going to be negative g j. Okay? How can we go from acceleration to velocity? Well, velocity is dx on dt. And the way we go from here to here is we've got to integrate both sides. So if we take our acceleration function in the x direction, if we integrate that with respect to time, we're going to cancel out one of the derivatives. So we'll integrate this side with respect to time, and we'll do the same thing here. So we'll have integral of d L squared dt. Now, this is where things are going to get a bit tricky, because we're going to have these plus c's. So this here we know is going to be our velocity, because it will be dx dt, so which is another way to represent velocity. So I'll move that real quick. Velocity. We're going to just have a c here, but we're going to work at that c in just a second. And this here will be our velocity in the y direction. So I'll say that's x, velocity in the y. Will be negative g, t, plus some constant. Now, these constants are our initial velocity. So if you were to set t equal to 0, this would give me my initial vertical velocity. Now, the reason why there's no t here is because the horizontal velocity we're assuming is constant because we specified there's no acceleration. So if there's no acceleration in this direction, that means it has to be moving at a constant speed. So the way we can find it is using pretty much our initial conditions here. So all we got to do is pretty much break this into vector components. So we have 15 meters per second, and it was shot at an angle of 30 degrees. Oh, that's not 30. So all we got to do is find the sides pretty much of this triangle here, because this is a vector, this is a velocity vector, so we'll have an x component and a y component. So this here will be my, when time equals 0, v of y, and my v of x, when time equals 0. So if I went t equals 0, that's still going to have my plus c here for the x direction, but when I have it here, it's just going to have c, because that will cancel out when time equals 0. So, way we find this is using trigonometry. This is my opposite side, so this side is going to be 15 sine of 30 degrees. So in other words, it's going to be 15 over 2 meters per second. Because sine of 30 degrees is a half. Here, this is going to be 15 cos of 30 degrees. So this is going to be 15 root 3 on 2. Okay? When time equals 0. So what that means is my plus c here, my dx dt, is going to be 15 root 3 over 2. And here, this is going to be my plus c here, so dy dt is going to be negative gt plus 15 over 2. Now the reason why this cancelled here is because I want to find the c when t equals 0, because that's the definition of what this is. This is the initial velocity when it takes off, the x component and the y component. So the way we found those t's was to substitute t equals 0. When we substitute t equals 0, this didn't change, so that's still my initial velocity, but this changed here because that cancelled out, which left me with this as my plus c. Okay, so that means my vector equation for velocity, so r just with one dot, is just going to be 15 root 3 over 2i plus all this, so negative g t plus 15 over 2j. Righto, we're almost there. So all we got to do now is pretty much remove a lot of this stuff now because we don't need it anymore. So I'm going to write my velocity equation just up here so I don't forget it. 15 root 3 on 2 I hat. Yeah, I'm not going to have room up there. I'll write it up here. So r dot t equals 15 root 3 on 2 I hat plus negative gt plus 15 over 2 j hat. Okay? Alright, so I'm going to get rid of that now, and I'm going to get rid of this now as well. Don't need that. Don't need that. And don't need that. So from this vector equation here, we know that the velocity in the x direction is this here, 15 root 3 on 2. And the velocity in the y direction, so dy dt, is negative gt plus 15 over 2. Now, I want position because that's what I'm looking for in this question, my position function over time. So the way we do that is pretty much we integrate both sides again with respect to time. So dt, dt. That's a terrible integral, but it doesn't really matter. So that's going to turn that into just position. Integrating a constant, you just add on the variable to the side and you plus a c. So 15 root 3 on 2 time plus c. Now we'll come back to the c in a second, and this side will be y equals, integrating this, add 1 to the power, divide by the new power, so it will be negative gt squared on 2 plus 15 over 2t plus another constant. Now, what are these constants? If I set t equal to 0, they are my initial positions. Now, this was started from a height pretty much. So, what we can say is this is our origin point if we wanted to, or we can say this is our origin point. Now, it's going to be very specific because it will change your answer overall. I'm going to say the origin point is here. So this is 0, 0. This must be then 0, 10. So when time equals 0, my height in the x direction is still 0, but my height in the y direction is 10. So that means when I substitute t equals to 0 in here, my c would be 0. When I substitute t equal to 0 in here, my y will be 10. So in other words, my c will be 10. So therefore, my vector equation for my position, I'll just move this, is going to be r will be 15 root 3 on 2t plus nothing because there is no initial position because we've specified this is my origin point, I hat, plus all this, negative gt squared onto plus 15t onto plus 10. And that's my vector equation for pretty much this path here. Now, let's say we want to find this distance it pretty much went horizontally. So the way we find that is pretty much, well, let's take a look at the vertical position. The vertical position here is 10. The vertical position here will be 0. So if we can find out what time that is, the time will be the same for both of them because both the x position and y position depend on time. So this here, we can mark, all right, time is 0 here, and time is also, not time is 0 here, sorry. My y position is 0 here, and my y position is 0 here. So all I got to do is take this equation here and just sub y equals 0. So 0 equals negative gt squared onto plus 15 on t all over 2 plus 10. Now, you'll probably need your calculator or the quadratic formula because it's going to give you two answers pretty much. I'm going to be lazy and use my calculator. So I'll go option, we'll go negative 9.8 x squared on 2 plus 15 on 2 x plus 10. Right, so it'll give you two positions pretty much. So time equals 0, add a couple of things. So it will be after 2.38 seconds. So if you want to find this horizontal distance here, all you got to do is pretty much substitute this number into this vector equation, because if you were to sub it in, this whole thing would be 0 because that's one of the solutions when it's a 0. And if you sub it into here, you'll have 15 root 3 on 2 times by 2.38, sorry. So 2.38 times 15 root 3 on 2 should give you roughly 30.91 meters. And that's the distance traveled. So that was a projectile motion question done using vector calculus. Yeah, very similar, very physics-based topic, but a lot more math involved. You can solve them using the Suvat equations, but this one is much better because it gets you more hands-on with it. Alright, all good.